Good morning, everyone, and welcome to SeptembRSE presentation session 4. We have 3 presentations in this session. A reminder that we'll have a short break in between the second and third presentations. You can ask questions via Slido, link in the chat. Immediately following this session, if you wish to stay on for the blended session hosted by the University of Sheffield, then please just stay on this Zoom call and it will start following this session. So without further ado, our first speaker in this session is Matt Williams, who's going to tell you about making clusters in the cloud. So over to you, Matt.
Thank you very much, Andrew. So welcome everyone to my talk on cluster in the cloud. I'll just get myself set up, screen shared, and all that stuff. Which one am I sharing? That one. Okay. So hopefully that's now working. And I've lost the Zoom chat, so never mind. It'll be a moment. So let's go back to the main slide. So I'm going to just do a quick walkthrough this morning of the tool that I've created with some help from other people at Bristol and some industrial collaborators called Cluster in the Cloud. I'm going to start just by giving a very brief 1 or 2 minute introduction to what it is. Then we're going to dive in and actually see how it all works and show off, the actual process of setting one up, running some jobs, doing all that sort of stuff. So Cluster in the Cloud comes from a core problem that we at the University of Bristol were seeing, that us as research software engineers, we were finding that various researchers at the university were being given cloud credits. And that in itself, of course, isn't a problem, whether they were getting them for free from industrial collaborators or whether they were applying for them in funding. They didn't always have a good sense of how to actually go ahead and do things with them. They were used to using HPC systems and so on, but they get their cloud credits, they log on to the cloud environment and they see something that looks like this. It's just setting after setting. You've got to understand networking and subnets and security and all sorts of things, which most researchers shouldn't have to know. What they do know is their research. They know how to do their particular field of research. They know how to program in Python or R or use particular tools. Many researchers also understand how to use batch cluster systems. Most universities have some form of free at point of use cluster computing system. And of course, there's the regional and national systems that many researchers also have access to as well. So they're used to working in that kind of environment. And the cloud is another paradigm shift, which they'd have to change to and learn and work out how to adapt to. And it requires a whole new set of skills, what are effectively system administrator skills. And we can't expect researchers to learn those skills as well on top of everything else. Now, luckily, many of us in the audience today and watching this video later are research software engineers. We're used to being in this kind of environment where we know that we can be the ones to provide those skills to the researchers, to bridge that gap between what they know and what we know. And so what we decided to do with Cluster in the Cloud was to make bridging that gap easier. I see Cluster in the Cloud really as a tool for research software engineers to help researchers make the use out of the cloud resources that are made available to them. So we give the researchers what they're used to, standard programming tools, Python, R, etc., running on a batch system, much like they have at their institution, but available on cloud resources where they get various benefits, such as not having to fight with people in the queue and only having to pay for what they use. They can burst and turn stuff off when they're finished, and they don't have to pay anything more than that. And at its core, that's what Cluster in the Cloud is. It's a tool providing that interface. So I'm just gonna I was gonna see if I could get the chat showing so that I can see if anything comes up. I will be taking questions at the end via Slido anyway, but just in case anything comes in while I'm going along or I'm waiting for something to run, I can always grab a question or two from the chat as we go. So here we are. I'm sitting at a plain old terminal. This directory is almost empty. If we do an ls, we see, well, there's one folder already sitting in there. That's a cluster I've pre-prepared, which I'm going to switch to in a bit. But the first thing I'm going to show you is the process to go through to make a cluster completely from scratch. So you've got to imagine that you've just been given some cloud credits. In this case, today, we're going to be doing it using AWS. But Cluster in the Cloud also works on Oracle Cloud and on Google Cloud. I'm currently in talks with a few people about getting it working on Azure. So some people have offered to help out with that. We've even had questions about getting it running on IBM Cloud, but that's a little bit further away, I think. So I've got some cloud credits and I want to run some jobs. I'm going to bridge that gap between the two. So I will go to, let's bring up the Cluster in the Cloud documentation, and it has a section there on creating the Cluster in the Cloud infrastructure on AWS. So the first thing that I need to do there is get my AWS credentials all set up and working. Now, AWS provide a command for that, AWS configure. You put in your credentials that you get from the web interface. I won't go into the details of that. That's the AWS side of things. But once you do that, you are now effectively logged into AWS on this computer. So I have run this command already. I won't be typing in my credentials live on a recorded session, but I've done this already. So you have to do that yourself if you were doing it otherwise. The next step is to download a installer script. I've been working recently to try and make the process of creating and destroying these clusters as simple as possible. So with a wget, I can download the install script. And I'm also going to download the uninstall or destroy script as well. So now I've downloaded those two. I've got these two Python files, and today I'm only really going to be using the install script, but we should be able to get that working. So we run it with a Python install Cluster in the Cloud AWS, and it knows how to do everything else. It's going to automatically download the tools that are needed to get things working. All you need to do is be running on a system where you've got SSH installed, and I think it only works on Mac and Linux at the moment, because Windows is always a bit trickier with those things, but it's all ready to go. If you don't have a system, like if you're running on Windows and this doesn't work, you can use the AWS or other providers' Cloud Shell. So for example, looking on the AWS interface, they have this little button up here at the top called Cloud Shell, which lets you run a terminal on their system running Linux, so you don't have to do anything on your own computer. But we just press enter and it's going to do stuff. It's going to churn through downloading the configuration for setting up the cluster. It's going to download a program called Terraform. Now, Terraform is a thing that handles the creation of the basics of the cluster, the login node, the shared storage, those things which you need in order to get something done. I'm going to let that run for a minute and just to go onto the next slide while that's running in the background. It takes around 10 minutes, maybe 15 minutes to get a fully up and running cluster. So in a 20-minute walkthrough, haven't got time to wait for it. So I will be switching to one I prepared earlier. So just while we're waiting for that to come together, let's have a talk of the key features of Cluster in the Cloud, the things that really kind of, I think, set it apart from some of the other tools out there, and the things that really make it useful for me. So familiar, I think, is one of the main ones. This was the leading reason for doing this. We wanted to make a tool which gave the environment and the system that people are used to running in. It's versatile, so you can run large nodes, small nodes, GPU nodes, ARM nodes, all clustered together, combine them in any way you wish. You're not restricted to one particular kind of compute node, which is one of the main things that some providers don't easily provide. It's dynamic, and so the nodes turn on and off only when you need them. That means you're only paying for the time that they're turned on. They get destroyed when they're finished. It's cross-cloud, so if you're working with researchers with AWS credits and Google credits and Oracle credits, you as the RSE can use the same tool on all the different platforms and make their life easier and make your life easier. And it's completely free and open source. You can access it under the MIT license, and you don't have to worry about anything more than that. So this is running, and at this point I'm going to switch over to one that I prepared earlier. This is going to run through, and when it finishes, it is going to show something that looks a little bit like this. It's going to give you the output of Terraform at the end here. It's uploaded some configuration onto that cluster, and then finally it's given your cluster a name. Now every cluster gets a name auto-generated by Terraform. In this case, the one that I prepared earlier is called Assured Unicorn. The one that's currently being created is called, let's have a look, it's always fun to see what it's calling them. No, we'll find out at the end because I can't see where the setting is. It'll tell us at the end. So every cluster has got a unique name. So you can have multiple clusters all installed at the same time, and they'll all be siloed off, independent from each other, even if they're running in the same AWS environment, for example. So let's log ourselves in, and we are there. So the first thing you need to do on a new cluster is set it up so that it knows what kind of nodes you want to run. And you do that by creating a file called limits.yaml, or it would be if I could spell. And you put inside here the list of the nodes that you want to create. Again, all of this is in the documentation. So as we go through finalizing the setup, there's a section here on AWS, and it gives some examples. So let's just make a simple one with some T3A mediums. That's a particular shape or size of node that's available on AWS. You can have as many different types as you want here. We could have extra large and all that sort of large as well, but let's keep our cluster simple today. So we're saying our cluster at most will only have 3 of these. And this is just a mechanism to help you have a bit of control over controlling how out of control your cluster can get. It's not going to balloon up and spend all of your money by making 10,000 nodes. It's elastic within the constraints that you choose to set. With that done, we can run a command called finish, which applies that configuration, sets everything up, and is ready to make those nodes. I'm going to wipe that to the top so that everything's near the top. And at this point, we can run the standard sinfo command, which is the standard slurm command. This is all running slurm in the background, which lists all of your nodes. And we run that, and it tells us we have 0 nodes. Nothing is there yet. All Cluster in the Cloud is doing at the moment is creating nodes in potentia. They are ready to be created, but they don't actually exist yet. And that's good, because it means you're not paying for them yet. So I've actually provided a separate command called list nodes, which lists all of the potential nodes you have. You see they're all named after the cluster you're in, the type of node, and they've all got a number. And in Slurm, idle and then the tilde means this is currently turned off. So it doesn't actually exist yet. It's not just turned off, it's destroyed. In the cloud, it just doesn't exist yet. So let's have a look at the process to run a job. Let's get that going. About halfway through, so I think we're doing okay. Let's carry on through and let's add a user. I'm going to copy this command because there's a lot of different settings in there, but I'm running a script to add a user, giving it a username, giving it a real name, and telling it which public keys that person can log in with. At the moment, I'm logged in as the CITC kind of admin user. And when running jobs, you want to be running as actual humans. So this is the sort of command you'd run for each of the researchers that you want to add to your system so they can get on and run jobs as a standard Unix user. So we can then log out and log in as me. And because I've already got my keys set up, I can log in and I'm all the way in. So there we go. You can check where I am, and my home directory is on this shared file system. It's a shared file system accessible by the login node and accessible by all of the compute nodes. So it's just one shared NFS style file system. It's not a high performance file system, but it's plenty good enough for running commands from and accessing small amounts of data. Anything faster than that, you're going to want to run stuff locally on the node using the local fast node storage, or set up a more performant file system as a layer on top of this. So let's make a job. We're going to make the world's most boring job for now because it keeps things simple. We are going to make a job which does just running the host name command. And the host name command is a command which prints out to the screen what node we are currently sitting on. So it's hopefully going to print out, when this job finishes, the name of the computer that our job runs on. If we look at where we're sitting at the moment, on the login node, we're at management.assured unicorn, our job is hopefully going to give us something a bit more interesting than that and actually say, I run on this compute node. Let's get that running with sbatch and then the name of that script, and it's submitted it. And it's at that moment there that I press enter that the main magic of cluster in the cloud happens. We can have a look at list nodes and we'll see that this node here, assured unicorn T3A medium 01, is now allocated and it's hash, which means it's in the process of being turned on. So let's again just quickly switch over to a slide and show how this works with a picture, because that's a bit more interesting than just watching the terminal sit around. So this is the environment we were in, but a few moments ago, my local laptop is connected to the login and management virtual machine in the cloud. As soon as I submitted that job with sbatch, it's gone away and it's started and it's made a new node sitting in the cloud. It's currently in the process of being turned on and configured, but as soon as it's turned on, it's going to start running that job and processing the data, doing that really complicated hostname thing that I asked it to do. If we submitted more jobs, it would create more nodes up to that limit that we set. It's going to try and run things in parallel to get your answers back to you as soon as possible. As soon as any particular node no longer has any work to do, they are going to run out of work and turn off. And then once all of the jobs are finished, maybe at the end of the day, if you're running short jobs or if you've set them running for a week, after that time, they'll all turn off and get destroyed again. And you go back to that basic small environment you had at the start. And one of the big reasons that we've set it up this way is to keep those costs down, to make sure that you're not spending all of your money and you're running out of everything far too quickly. So as an example of running a whole bunch of jobs in parallel, if you set up 40 nodes all in parallel with each other, it would spend maybe a minute or so on each node setting them up. The y-axis here is the state of the number of nodes. Each job in this situation, on the example I'm showing here, runs for about 5 minutes. In reality, your jobs are probably longer than that. Once your job is finished, the cluster is going to hang around waiting for your job to, for any more work to come along. So there's a little bit of a buffer time, which allows you to avoid paying that turn on, shut down overhead if you want to just keep it waiting around because you know you're about to submit another job, and it will slot straight in and start running straight away. So looking back over here, let's have a look at our nodes. Our node is now idle. If we look at our job information, it tells us that job 2 that we just submitted is now completed. And we can have a look at the output, and the output of that job has indeed created something which has got the name of the node that that job ran on, and that's all working correctly. So that's the core workflow of all of this. That node is going to hang around for another 5 minutes or so. By the time I finish answering questions, it will have been destroyed and I'll no longer be paying for it. And I'll just be paying for that core little bit, which costs something like £1 a day, maybe less than that. It's a relatively cheap core part of the cluster. I've got about 2-3 minutes left, so I'm just going to tell you about 1 or 2 last things that that the cluster can do. So if I log back out and I log in as the admin user, actually let's pop back to our new cluster that we were creating and see how it's come on. There we go, it's already finished. So our one that we started creating at the beginning of my talk is called itself Destin Cicada, and I could log into that and do the exact same workflow that I've just shown you. I've just time shifted a little bit. So logged in as the admin user, one thing that you'll see in the home area here is a file called compute image extra, which if you look inside it, then you'll see that there's a bunch of commented out stuff. But this is where if you want to configure your node image, you do so. So if, for example, you wanted to have the development tools installed on your node images because you want to do compilation there, or if you wanted to give access to the easy software store that's available via CVMFS, you could do that there as well. And to make that work, you go ahead and you run. I'll do this because I'm not going to have time to wait for it to finish, so I might as well kick it off. It's going to go away and it's going to make a new node and it's going to start running all this stuff. It's going to create a new image so that any new nodes that we turn on from this point on will have access to that software that you've added in. This is the same way that you would include GPU drivers, things like that. So if you want GPU nodes, you can do that through this interface as well. And any other configurations you want to do. So Singularity, if you want to enable Singularity on your compute nodes, just a yum install Singularity here will immediately give you access to that. And we've used this to great effect in the past. So very last thing that I'll show is the management console in AWS, so you can see what's happening. You'll see I've got 2 management nodes, one for each of the 2 clusters I created. I've got my compute node, and I've got this Packer builder. That's the thing that's generating the compute image for both the new cluster, that command I just ran, and the cluster that we created at the beginning, which is still going through its initial setup phase. So just to wrap up, the performance characteristics of cluster in the cloud is best suited for kind of high throughput stuff, not necessarily your large scale 10,000 node MPI jobs, but it's really, really good for that standard, just churning through array jobs style batch throughput computing. One place that we found it really beneficial is for teaching clusters. So if you want to be teaching HPC or something around that area, creating one of these in the cloud as your teaching environment means that your students can't mess up your production environment. They can't break anything, and you just destroy it again afterwards, and everything shuts down and disappears. So thank you very much. Link to the documentation is there. I'm always around on Slack to answer any questions and things like that. And I want to just thank AWS, Google, and Oracle, both for sponsoring this conference and for supporting my work in this, and all the people who have helped me with Cluster in the Cloud. Thank you.
Thank you very much, Matt. We will move over to Slido and see what questions you've got. Oh, 7 questions. So the top one there on Windows, I guess that WSL might also work.
Yeah, absolutely. It has relatively small requirements from the laptop side. It's basically just it needs SSH, I believe. So definitely WSL would work. That's a good option.
There were quite a few questions about what you can change after you've set your cluster up. So can you change the limits for the size of the cluster later, or is it fixed once you've done it?
No, you can absolutely change them. So you can add in new node types. If I was running a longer walkthrough, I would have shown adding in ARM nodes, the Graviton 2s. You can just add them in at any time and set whatever number you want, make it larger, make it smaller. It's flexible like that.
Great. What work is needed to get it working on Azure? How can people help you?
So the main issue we have with any new provider is having cloud credits to get the thing working in the first place, and secondly, having long-term cloud credits in order to fix bugs and do maintenance. Now, I've got a few contacts that have grabbed me on Slack, so I've got a team, and I've forgotten the person's name, but they're looking at perhaps getting this set up on AWS, on Azure, because they want to use it there. And I've also had some offers of putting me in contact with people who can get the long-term cloud credits so that we can maintain it on Azure. So if you want to help, just message me on Slack, on the cluster computing or personally, and I can always loop you in if we need help.
Sounds good. So there are a few questions here about installing software and what software you support. So do you support Docker or Singularity?
Yeah, so Singularity, I mentioned that, it's easy to install. Docker's not set up, but Singularity and Podman are pretty trivial to get set up. You sometimes need a small amount of sysadmin experience to get the things configured, but it's a relatively simple job, and it's the sort of thing where I want to put a how-to together for it. So give it a go yourself, let me know how it works, and then we can write some documentation for it.
Okay, and I think you mentioned both Jupyter and Dask, but just to answer the question again.
Yeah, so we've got a script which can automatically install Jupyter Lab and Jupyter Hub all set up, and it puts Dask in there as well. It kind of works, but it needs a little bit of tweaking to make sure that the job submission scripts are all linked together. It's a work in progress. If you know how to do it yourself, it will work. Otherwise, it's something I want to make smoother.
Okay, and I think you covered this on your final slide, but can you run multi-node or MPI jobs?
You can. It's just not going to be the highest performance using standard cloud networking. So you're not talking InfiniBand style necessarily. You get unpredictable latencies as you would ever, going between data centers on the cloud. But it works. So depending on how much communication you need, it might suit the job.
Okay, I know another control question. So how long they stay on for 5 minutes, you said, I think?
I think 5 minutes is the default, but it's a configuration option you can change. It's not well documented, but you definitely can change it. You can set it to 0, you can set it to 2 weeks.
Okay, the final question on here, how does cluster in the cloud perform compared to on-premises clusters in terms of performance?
So that's really down to the cloud providers. We're not adding anything in between you and a standard cloud virtual machine. So you get standard cloud performance. We've had some groups here at Bristol using cluster in the cloud to do benchmarking of the cloud, of new hardware and things like that. And they were finding good and predictable performance. So you don't pay anything extra for using cluster in the cloud, except the time it takes to turn on the node, which is always going to be shorter than your queue time. So you don't pay much.
Yes. Right. Thank you very much, Matt. So I think without further ado, we will move on to the next speaker, who's James Robinson. He's going to be talking to us about secure data analysis. So take it away, James.
Hi. Let me just get my slides up. Great. Can everyone see that?
Yep, can see that.
Okay. Yeah, so I'm going to be talking about secure data analysis in the cloud. And specifically, I'm going to be talking about the Alan Turing Institute's Data Safe Haven project. So I'm going to cover a couple of things here. So what is the Data Safe Haven? Who's using it? What is it that's unique about it? And finally, what are we planning to do in future? So starting off with what is the Data Safe Haven? So there's a couple of different things, really. It's one part of it is a framework for agreeing data sensitivity. So we classify different projects into one of 5 different sensitivity classifications. It's a software-defined, reproducible deployment to the cloud. So this is currently Azure only, but we are open to expanding it to more clouds in the future. It gives you an isolated, secure research environment. Sometimes these are called trusted research environments for each project. And the hope is that we can help people maximize the productivity on working on sensitive data sets while minimizing the chance of a data breach. So going back to the classifying data, our classification is based on the idea of a work package. So that's a particular data set or multiple data sets, plus the analysis that's being performed on them. So you could imagine, for instance, that you might have a data set where the analysis you wanted to do produced a more sensitive data set. So for example, if you had a load of like phone location data and you used it to identify particular people and where they'd been, that would probably be a more sensitive output than the input. And of course, it's easy to think of examples of things where the output is less sensitive than the input. So really, it's important to have these two things as part of the sensitivity classification. As I mentioned before, each work package belongs to one of 5 sensitivity tiers. Tier 0 is the least sensitive, and up to tier 4, which is the most sensitive. And when classifying the project, we need agreement from someone who's a representative of the person providing the dataset, an investigator who's responsible for using the dataset in the project, and an independent expert in handling sensitive data. And they need to all agree on which of these sensitivity tiers it falls into. So we have a flowchart, which this is a very simplified version of it here, about where you come out to on these different tiers. The idea is that everyone will work through this flowchart, or the slightly more detailed version of it that we use in real life, and will hopefully agree on the sensitivity of the projects. And if there's any disagreement, they can discuss that among themselves and hopefully come to agreement on where the project lives. So we require various different sort of security measures at these different tiers. And the idea here is that we want to make things as easy and usable as possible. So we can imagine for very sensitive data, you need a lot of, quite a locked down environment. But for less sensitive data, there's no reason to not do things in the open. And so here's our sort of table showing how we increase the security controls as you go up through the tiers. So for example, here at tier 0 or tier 1, this is basically something you could be doing on your laptop. If the only reason you might want to use a secure environment is perhaps if the data set is very large or something and it's too big to use locally. Then up at tier 2, we start having more restrictions. So here, for instance, we use an isolated virtual network, and we don't allow outbound internet, and we only allow inbound connections from particular known allowed IP addresses. Tier 3, we try and require also some physical limitations. So in the past, pre-pandemic, we've been able to say, well, we'll only allow access here in particular physical locations. And then at Tier 4, this is, you need really high physical security and so on. So we're mainly focusing on Tier 2 and Tier 3. What we've defined as being Tier 4 is things that perhaps, like a nation state might be interested in, and we don't feel that we're able to come up with sufficiently secure setup for that. But Tier 2 and Tier 3, we've run several projects that fall into this categorization. So I'm going to discuss briefly what the architecture is, and then perhaps what the user interface looks like. So essentially, we have one shared management area that talks to an Azure Active Directory, and this deals with user management, and it also deals with a couple of other centralized things. So for instance, we have mirrors of PyPy and CRAN to let people install Python and R packages. And then this management area can have several different secure research environments, each of which is isolated from any of the others. So this is what the management area looks like. I'm not going to go through this in detail, but essentially it's got a couple of different virtual networks. One that deals with each of sort of two different tiers of these package mirrors, because at Tier 2, we allow any package in PyPy and CRAN, so we just use a proxy. At Tier 3, we only allow specific allow-listed packages, so we use a slightly more complicated setup where we pre-download those specific packages. And then the main part of the management area is just a domain controller and network policy server to control logon to the remote desktop environments. This is the diagram of each of the individual secure research environments. So you can see here, as a user, you have to go through some multi-factor authentication. You have to go to a particular URL, which, depending on the sensitivity tier of your data, is going to be locked down to only allow access from certain IP addresses. And then we support two different remote desktop solutions. So one is Microsoft Remote Desktop Server, one is Apache Guacamole. And depending on which of those you set up, you either need this additional VM here or you don't. And this then gives you access to as many compute nodes here as your product needs. So these could be CPU or GPU nodes. We don't currently support sort of cluster style workflows, but something we'd like to support. There are also then once you've remote desktop into these nodes, you have access to various shared services. So here we have CoCalc as a sort of collaborative Jupyter notebook, CodeMD, which is an open source version of HackMD, and GitLab for version control that's all inside the environment. And we also have these databases. We currently support Postgres and Microsoft SQL databases. This virtual network is completely isolated from anything else, so we have to have these private nodes here that sort of proxy through to the sensitive data that's stored in Azure blob storage or Azure NFS storage here. So this is the input data, and this is things like user data, so your home directories and so on, which means that these could be sort of automatically available across any different nodes in here. So if you deploy a new node, you'll get the same user directories, you'll get the same shared directories, and so on. So what does this look like in practice? So as I said, you log in with a password and MFA. So this is what the Microsoft Remote Desktop login looks like. So you need your username and your password. And then you get this remote desktop that's running in your browser. So it's a bit confusing to say this, but from this remote desktop running in your browser, you can't access the internet. So even though it's running in a web browser, it doesn't have outgoing internet access. So it just has, as I mentioned, these local services, and has access to the useful input data and various things like that. So of course, as I mentioned before, the access to the data is only possible from inside the SRE. So this is something that is very important, of course, to the people providing the data to know that the data is not going to be leaked anywhere. There's no way to get to it, to store it in your laptop or anything like that. It's only available inside this environment. And we try to make the environment as sort of usable out of the box as possible. So we have a lot of data science tools pre-installed. We have lots of programming languages pre-installed, so Python and R and Julia with a load of packages, and some others as well, which I forget at the moment. And as I mentioned, no internet access and no copy and paste between the secure environment and the user's computer, which you're accessing this from. So who uses this at the moment? Well, the main use case has been the Turing data study groups, and this is really where the whole project started from. So these are week-long collaborative hackathons, and the idea is to bring organizations with a particular data problem together with researchers who can hack a solution to that problem. So the idea is the researchers sort of brainstorm together and engineer some data science solution, and then produce some outputs, which is the code used to solve the problem, plus a write-up of the work that's been done, which can then be brought out of the environment, and the data stays inside the environment. So only the useful outputs are brought out. We also run with several sort of longer-term Turing projects. So these are things where we've got Turing researchers who are analyzing sensitive data, and we want to provide confidence to the external data providers, again, that the data isn't going to be available on someone's laptop or anything like that. So these have been particularly things like drug research, so where there's commercial sensitivity, or people trafficking, where there's personal sensitivity there. We've also been supporting several partner organizations, so helping them to set up and host their own safe havens. So we've partnered with the Health Foundation, with the University of Nottingham, with the University Hospitals Birmingham, and with the Francis Crick Institute, among others, to get them to set up their own safe havens using our code. So what is it that makes the safe haven unique? So I think the first thing is the control that you have over it. So you can combine data from multiple sources or data providers, because you're running this yourself. You can decide what goes into it. You have complete administrative control over the system, and you're able to deploy new secure environments or tear down old ones, at will. You have control over the data lifecycle, which is tied to the project lifecycle. So when the project's finished, you can delete the data and know that you're not at risk of any data from old projects sort of hanging around anywhere. You have some. The next thing, I guess, is confidence in the code. So the code is open; it's not yet public. That's something we're hoping to do later this year. But we've had it penetration tested a couple of times. We really hope that people who use it will inspect the code and contribute improvements back to it. We really want to build this out as an open source community project rather than a Turing specific thing in the future. And we've helped people to adapt the code to meet their specific requirements whenever it's needed. And then of course, the last thing is the cost. There are other solutions that do things like this, but they tend to be commercial solutions where you have to pay for the environment. There's no cost to this, no licensing charges. The code is MIT licensed. Really, the only thing you're paying for is the cost of the underlying cloud platform. In terms of Ingress, so that's bringing data and code into the environment. We require sort of secure transfer using Azure Storage, ideally Azure Storage Explorer, to bring that into the Azure Blob Storage. Then for usability, we have, as I mentioned, a wide range of data science tools pre-installed, which hopefully allows you to work in this relatively offline environment where you don't have outgoing internet access. We have copies of the Python and R package repositories and the ability to install additional software as agreed by each project. And then for egress, the data provider and investigator and referee have to approve any egress of any data or code or results. So again, the data provider has confidence that nothing is being done with their data that they haven't already approved. And again, we use the same secure methods to transfer these outputs back out again. And then finally, when it's no longer in use, the SRE is deleted. So this obviously covers the data, but also the analysis code, any work that's been done, any things that might have been accidentally stored in someone's home directory or something. The whole thing is wiped. So what are our future plans? So we're working towards several different certifications. So we're currently in the process of applying for the NHS DSPT certification. More long-term, we're looking at ISO 27001, which is a very sort of intensive security requirement. We're looking to improve our logging monitoring to make it a bit easier for the sysadmins to inspect a running safe haven. Currently, we work on the idea that data is brought into and out of the system at sort of discrete points in time, so at the beginning and end of a project, for instance, and therefore it's easy to adapt have our our approval. Each time stuff is brought in and out, we'd like to adapt this so it's easier to approve continuous data flow. So you could imagine, for instance, there might be data sets which are updated every day or every hour or something, which you'd want to include inside one of these safe havens. And as I mentioned before, we'd like to make the project public. So we've just done a recent penetration test. We're addressing a couple of issues from that, but then we'd like to make the code public and freely available to anyone who wants to use it. Please do use any of these methods to stay in touch with us. So we've got a Slack channel for general discussion and debugging and help. We've got a GitHub. So currently, as I mentioned, it's private, so you probably won't be able to see it. But when we make the code public, this will be the place you can get hold of the code. We've got an email address for contacting the developers directly, and we've got a newsletter here at the bottom where we will announce new releases and announcements, particularly, of course, when we make the code public. So finally, just some acknowledgements. So thank you to all of these people who've contributed in various ways, either through contributing to the code or contributing discussions about particular things we ought to be aware of, or legal issues or anything like that. We couldn't have done this work without them. And then finally, we've got this very nice picture that sort of tries to summarize everything about the safe haven in one cartoon. So I think I'll leave it here, and we can ask any questions that you might have about this.
Thank you very much, James. It's a very interesting and detailed post you had at the end there. Right, let's move on to Slido then. So I think you mentioned this a little bit, but about the running costs of a data safe haven.
Yeah, give me 1 minute and I will find our most recent costing model. So, okay, right. So the cost of the sort of management is around £2,000 a year, a bit under. The cost of running one secure research environment. I was incorrect there. So sorry. The cost of running the management is about. It could be as much as £1,500 a month. It depends on exactly how you set it up. So, for instance, the proxy version of these mirrors is much cheaper than the sort of local mirror. So depending on exactly your use case, it could be much lower than that. It could be like £100 a month, but it could be as high as 1,500. And then a standard kind of secure research environment, we reckon is about £500 a month. Just to remind you, of course, that the cost of the management sounds like it's a lot, but that's shared across n different projects that you might be running in one place.
Okay, thank you. Do you have any plans to support other cloud providers?
So we've been developing this on Azure because we actually got a large donation from Azure, and it's about to run out in October. So unfortunately, I mean, I would have loved to say to Matt that we could contribute some useful Azure credit time, but ours is almost run out now. But yeah, we certainly would like to support other cloud providers. Again, it's exactly the same thing that Matt was saying. It's coming up with some credits to be able to do that, and not just in the short term, but in the long term as well, so that we can actually actively support rather than just coming up with a single iteration that we know works at one point in time.
Okay, and the remaining questions all seem to be about management and sustaining things. So do you support data lifetime management, i.e. do you delete data after a set period of time to meet GDPR requirements, that sort of thing?
So not explicitly, but when you shut down the project and delete the secure research environment, it will delete the data as well. So in that sense, it's unlikely that you would have data hanging around once there's no one working on that. We tend to leave those sort of questions up to the individual institutes. So we have, at Turing, we have some GDPR guidelines and things like that, but we can't enforce those things on a technical basis. So we just provide recommendations. Okay,
how do you manage and sustain your project? Is anyone employed specifically just to maintain and keep up with issues?
So it's still really like a work in progress at the moment. We definitely have a lot of things we'd like to improve. For instance, one thing that we'd like to change some of the underlying technology a bit to maybe take a bit more advantage of some kind of like X as a service type things that Azure or other cloud providers provide. We'd also like to make a bit more use of Terraform than we currently do, for instance. But once we've got to a bit more of a steady state, then yeah, I think that would, those sort of things will be more our focus. At the moment, we've got, I think, 2 people or 3 people working half-time on it up until the end of 2022. Beyond that, certainly by that point, we'd hoped that it would have transitioned into more of a community project, but there might still be Turing involvement as well.
Okay, thank you. And the final question is there any auditing of the processes and the setup that you went through on a regular basis?
So we have, auditing of the technical things. So, checking that all of the guarantees that we say we provide, so, that you can't access the internet, or, different secure environments can't talk to each other, that kind of thing. We check those sort of things. I'm not sure if that really answers your question. So if you want to, whoever asked the question, if you want to expand a bit on what you want to know here, I'd be happy to.
Yes, whoever asked that question, we do have a little bit of time. So if you want to ask a follow-up in Slido, we can wait for it briefly if you want to. Or you can ask in the chat.
I mean, perhaps part of this, part of the answer to this is the the penetration test that we've just run. So we're hoping to in future run penetration tests on sort of the most recently released tag of the code every 6 months. And so we do sort of from scratch deployment, and we're working with the same set of penetration testers who, I think initially it's difficult to get people to understand that what we want is kind of the opposite of a normal penetration test. We're not so worried about people trying to get in, because we're reasonably convinced that you can't, but we are worried about people trying to get out. Getting that understanding with the penetration testers. Do you have a sandpit environment that we can play with? So certainly for Turing project, yes. We don't have one running full time, but yeah, for any, for onboarding of people that they're working on Turing projects, we do have a sandpit environment, but it's not currently sort of open to the general public, because one of the requirements of connecting to it is that you have to be connecting from the Turing corporate VPN. So I see a thing in the chat. The process is mentioned about who has to sign off on various data transfers, etc. Auditing would look at specific projects and check the processes were followed. Yeah, so we do have a sort of a separate project, which is around sort of recording data classifications and things like that. And we'd like to expand that to record these data transfers as well. But we don't currently have that. How do you deal with the analog hole? Yeah, so this is obviously a problem that you can't solve, right? I think in general, you have to assume that, perhaps you might be aware of the sort of the 5 safes framework, where like for secure products, you require sort of 5 different levels of safety, and one of those is safe people. So we hope that no one using these research environments is like maliciously trying to egress the data. We can't be sure about it, and we try to make sure they can't do it accidentally. I think in general, the data sets that people use in these sort of projects are quite big, and the idea of doing like screenshotting, even don't even need to go as far as a phone. You can just do a regular screenshot of your computer screen. You certainly could do that. You'd need a lot of like post-processing then to turn that back into usable data. But yeah, it is potentially a problem if you don't trust the people who are working on the project.
Okay, thank you very much, James. We will leave it there. And before our third talk, we will have a 5-minute break. So we will see you in 5 minutes. Right, welcome back to the final presentation of this session. And Flora is going to speak to us about crop and building a digital twin of an underground farm. So take it away, Flora.
Thank you very much, Andrew. Let me see, let me just share screen. Okay. Let me know if you cannot see my slides or the videos for that matter, because I have a couple of videos that I'm hoping to show you. See if we can start the presenters mode. There we go. Okay. Yeah, my name is Flora. I'm coming from the Alan Turing Institute, like James Robinson before. And I think there are quite a few presentations from us in this year's SeptembRSE, which I would definitely recommend watching them, because there are some really, really interesting projects happening at the Turing and at the engineering team at the moment. This project is called Crop. It's a project that I've personally worked for almost about a year now. There are three of us working on this project currently. There's Thomas Lauseskas from the team, and Mei Wong and myself. And we have a range of collaborators from Cambridge, also the company that we're working with, which is an underground farm. So yes, I'll explain a little bit about what we try to do by building this monitoring platform for an underground farm, and what does it look like. So what I'm going to talk about today is I'm going to explain a little bit about what is urban agriculture and how and where is applied in the world. I'm going to talk about the company itself, Growing Underground, the project. So there's a wider project which is called Urban Agriculture, and it involves installing sensors and getting data and so on. Crop itself, which is our digital twin, our prototype digital twin. The infrastructure, the analysis tools that we built, and this 3D model, and why we built a 3D model for this application. And also a little bit about future work and what we're going to do. Great. So why urban agriculture? Why should we grow plants in the city? So essentially, as urban populations grow and grow and grow, there's less and less space for us to grow vegetables, but also, there's deforestation and other stuff. So by developing systems where we can grow vegetables inside our cities, we reduce transportation costs. We don't have to transfer any type of crops from long distances away from the city. And also we can create available land for forests and reduce carbon emissions. So essentially what urban agriculture is that we are cultivating and distributing foods within our cities rather than rural areas. So it's kind of a paradox. It's kind of like combines both rural and urban at the same time. We can see here that it's really important because it's a trend that kind of, let's say, becomes more and more popular precisely because cities grow and grow, and the distances to travel products become longer and longer. And that creates costs for the companies, but also, it's all this carbon emissions from food miles. So basically what urban agriculture is doing, and this is a screenshot from the company itself that's growing vegetables underground, is using renewable energy. It's carbon neutral because it's located right underneath your house. It's crops grow in a controlled environment, so they are pesticide free. And you basically grow your salad without the sun, but in conditions that simulate the sun, using LED technology. And therefore they grow year round in perfect conditions. They also use nutrients to grow the plants, and therefore they have more nutrients. And they've drastically reduced the food miles for both retailers and consumers. So there's a number of projects of urban agriculture around the world, especially in Japan and in China. There are, they're very popular, something that's called horizontal farms. A lot of large architectural firms have created projects that they have even developed skyscrapers that are meant to grow vegetables and combine residences or office spaces and farms in the same space. It's something that will become more and more available in the future as technology grows. Here's a couple of more examples. This is in The Hague. The first one is a repurposed telecommunications building. So it's an entire building that they've repurposed to a vertical farm. And the second one is in Liverpool, the aquaponics system, which is designed by Farm Urban. And it's integrated on balconies in children's hospitals. But obviously, we also know some other urban farms ourselves where we kind of grow vegetables in our own balcony or backyard. There are all sorts of residential rooftops, either in Kathmandu or in London or in Greece or all sorts of places around the world. So this is the company we're working with, is called Growing Underground, is a repurposed World War II bunker. So it's like a huge tunnel that's located underneath the center of London in Clapham Junction, for those who know London. And what they've done is that they bought the tunnel and they've repurposed it to grow vegetables. Here you can see the initial state of the tunnel on the left-hand side and how the initial farm trials happened in the middle and how the tunnel is actually developed on the right-hand side. You can see that everybody who needs to go there. So we went and visited the farm, and you need to wear special clothes with all sorts of hats and boots and coats. This is literally a lab because it's a controlled environment, and there's a very high danger of infesting or of causing an infection of the plants, and therefore everything needs to be very controlled, done very carefully. So Yeah, and at the bottom here, you can see the final product where the salads are actually cropped and put in little boxes and distributed around the restaurants or areas around London. Now, the interesting thing about this is that literally the plants grow within 2 weeks from seeds to an actual plant. They're being harvested, and within 4 hours, you can actually get your salad in your bowl in your house. So the process is very, very fast, very efficient, and carbon neutral. This is the farm, which is located underneath London. So you can see the tunnel here. There are two different tunnels with 2 entrances, which is those vertical pipes, which is tunnels basically, and into two parts. And the red part is the current farm. The blue one is where I think the farm is going to be extended in the future. Yeah, it covers quite a lot of miles. And it has both growing areas and processing areas, but also research and development areas within the same tunnel. This is the model of the farm in 3D. So it looks like a pipe, but these are actually about 2 meters wide, 3 meters wide, the tunnels, and I'd say 3 meters wide. And then you have the entrances, the 2 entrances here. There is a connection staircase in the middle, and the 2 tunnels that they're growing the vegetables. Here's another ground view of the tunnel. So yeah, as you can see again, in the middle, there is the staircase where you go down 30 meters. This is an old bunker, so everything is really like a Victorian staircases that you go down. And then you have these old tunnels that have been repurposed as growing tunnels. There's a packaging and processing area, propagation tunnel, and the R&D area. The hydroponic system is basically like 2 arrays of trays, and they just run parallel in 23 different zones of 2 meters long. So what the farm has done in Cambridge to monitor the conditions of the farm is that they've installed a set of sensors to monitor the environmental conditions. There are a couple of Raspberry Pi boxes with temperature sensors and humidity sensors and air velocity sensors that's distributed around the farm. There are a couple of other types of sensors which are from a commercial company called Zenzi, which are also distributed in the farm. They also measure temperature and humidity. There are fans that need to control airflow, and whenever there's high humidity, you turn on the fans. They're installed in 3 different parts of the rack. So we have one on the top shelf, one in the middle, one on the bottom. And therefore, you don't just have like sensors on the horizontal axis, but also on the vertical axis, which is where the 3D is now taking place. And this is another view of the tunnel. We have incoming air coming from the staircase. There's the entrance, the front of the farm, and then it goes all the way to the middle of the farm here. And there are the sensors in the front of the farm where we measure air velocity. There are fans around the system around the area where they kind of regulate the airflow. And there are temperature, humidity, and CO sensors located both in the entrance of the tunnel, but also in the main part of the tunnel. So regarding the project itself, there are not that many of us working on it. There's 3 of us from the Alan Turing Institute, as I mentioned before, Thomas, Mei Wong, and me. There is Rebecca Ward and Ruchi Judhari from Cambridge and the Alan Turing Institute that they're leading the project. From Cambridge, there's also Melanie and Paul. From Growing Underground, which is the farm itself, it's Jacob and Richard, and there's also an external co-worker, which is Catherine Leaning. So I'm going to talk a little bit about the project aims. What we aim to do is we need to gather all the historic and new real-time sensor data that are coming from the farm. We wanted to 3D visualize the sensors and tunnels so that we can communicate it back to the farmers, but also to the scientists who will do the data analysis. We wanted to create a platform that connects models that were built from Cambridge, so prediction models of crops growing, temperature, and humidity. Develop forecast scenarios of the farm. So what would happen if temperature rises? What would happen to the crops? They stop growing. And then we also wanted to produce some in-depth visualization plots and therefore kind of create like a holistic monitoring platform for the underground farm. Now, the difficulty of this project is that you're not actually developing a project from scratch. So nothing is brand new and shiny and we can choose what to do. They're already installed systems. Some are really, really old. There's old infrastructure. The actual structure of the tunnel needs to be taken into account. So the building itself. So there's a lot of old infrastructure we need to integrate in one new system and also understand what are the limitations and what other potentials there are to monitor this farm better. So what we had at the moment was some custom Raspberry Pi sensors, which Cambridge had installed before. Some worked, some didn't work. So there was another challenge there. There were already collected historical and aggregated data from the previous years. And we also had new data coming from energy, for example, where we had to connect to a Stark web page was an API that we had to link to get energy data, but also weather data and other real-time data coming from other sensors. So it was a lot of different and diverse infrastructure we had to connect to one system to kind of make it see what's happening. And the semantic representation is this one here. So we had like a bunch of custom sensors. We had the 30 megahertz, which was the commercial sensors API. And we had to link it to with the energy API, the weather API, and some Google Sheets that the farmers themselves were writing in terms of monitoring crop growth. So what we did is that we connect them all in one database, which we connect the database with our crop platform. And then we connect it to the Cambridge modeling and data processing. And then we connect them back to the database and we use the platform to visualize this data in return. So there was this loop that went around to get all this information, process them, create some predictions, and then store them back to the database. So what is CROP? CROP is the prototype digital twin. What I find interesting in this project, why I wanted to show is that, is because there is a question now, how do we actually create digital twins for urban infrastructure and for cities? Because as I said before, cities and urban infrastructure is quite old in many cases. There's also the physical structure that needs to be taken into account. And how does that work in terms of creating a digital twin? So what we try to do here is we try to create crop in a cloud-based application to make it flexible, customizable, to make it open. So the code is online, everything is built procedurally. So The database is built in SQL Alchemy, where anyone can just recreate it quite easily. But also be custom made enough to fit the very, very specific needs of this particular project and Growing Underground, which is the company that we were building it for. So how did we build this architecture? This is the chart that we've created. So on the left-hand side, we have the database with the historical information. So the previous database that the Cambridge University was using. We have the Raspberry Pis, which are collecting real-time data from the sensors inside the farm, Stark Energy data, and the Zenzi sensor data that are coming from the commercial company with the commercial sensors. All of these, we put them together and we link them to an SQL database. We have enabled we're developing some ML services to process this data, and we are, publishing it on the web application that we're building as Crop. From the database, we have also enabled some notebook facilities so that researchers can perform analysis, Storage Explorer, obviously, and they're all linked to a user system where with 4 different types of users, so administrator, public, and the people from the Growing Underground, the farmers themselves, with different levels of accessibility. So Crop is the main interface of the digital twins. Users can explore all these collected heterogeneous IoT sensor data and use the developed 3D visualization tools. Crop, the database itself is constantly updated from the IoT, from the sensors. And we're trying to integrate some machine learning services to create some automated prediction and calibrated models into the platform, which we're doing currently. I'd like to show you I'm going to pass this on very quickly. These are some data visualization that we did from the sensors that we collected, just to show that in order to communicate information to a part of the audience, you may have to do some processing. You can't just put some time series data there. So here, for example, we had a chat with the people in Growing Underground and figured out that actually it's more useful for them to see how many hours per day is the farm being hot, how many hours per day is cold, and how many hours is being really cold, rather than seeing this time series data. And what we tried to do when developing dashboards is actually produce diagrams that would very, very quickly, in a matter of seconds, kind of communicate that information. So this, for example, is something like this. So you can see very quickly within a month's time how much time the farm spent that was quite hot, that was a bit, normal temperature or cold. Similarly, we did that for the lights and energy. So instead of having an energy time series data, it was more useful to kind of run some calculations and see how many hours lights were on during a certain period. So these were quite useful visualizations for the farm to communicate. Again, similarly for the using energy data and calculating fan speed and how many hours was the fans turned on and how low or high it was. So I'm going to jump to the platform itself. So the interesting thing about Crop is that it's not just, we didn't only have to have a visualization of the sensors, but we had to keep monitoring the whole environment within the farm itself. which means we had to take into account the structure of the tunnel, which is located 33 meters. To do that, we had to create a 3D model of the tunnel, visualize it, and also run calculations on how temperature is distributed through the walls and from the walls to the vegetables themselves. So how did we do that? We developed a web app where you could actually see the entire farm. You could do virtual tours, so you can jump from one tunnel to the other. We could visualize very fast the state or the growth of the crops themselves, and also the sensors. And I'm going to show you a little bit about what we used for that, and then a little video of the farm itself. So for the software stack, we used Flask. We used Jinja 2 for templating, Python for the backend, Unity and C# to develop the 3D model, JavaScript for front end and HTML, obviously, SQL Alchemy and Postgres for the database. We do have the platform running at the moment, but you do need a password and a username. So sadly, you cannot access it yet. But it's currently running and it's looking like this. So this is a fully interactive 3D model. You can navigate, you can rotate around. Then the web app is a set of interactive charts where it's easy to visualize. It's easy to understand the different parts of the farm and how hot they were, how cold they were, coming from the database. There's a way to explore each sensor individually or each part of the farm individually. This is the energy usage analysis dashboard. And the air change per hour. I'm going to go fast. We can select different times, different dates, and obviously explore the data themselves. I'm going to go to the, now for the, I'm going to first show you the, go ahead and show you the 3D model first. The 3D model contains the main farm itself, but it has essentially 2 levels of detail, which you're going to see in a minute.
Hi, Flora, if you could wrap up in the next few minutes, because we have
Sure.
a hard deadline at 12 for the next section, so thank you.
All right. So there we can see the real-time information of the sensors. I'm running a bit late. The second level of detail is as we zoom out, and you can see the entire farm underneath the Clapham Junction. And then we can also produce heat maps of the temperature around the farm through an aggregation of the sensors, humidity, airflow, etc. And energy, I think we have at the moment. Right, okay, so I'm going to wrap up by saying, just showing the charts of how this is done in 3D model. So we have the graphical model of panel 1. We're instantiating a single array of cells for the locations, where we do a request for sensors and we store them back to the locations. Then we create a request for the sensor readings, instantiate the sensors in the 3D model. We generate health bars for the sensors and how well they're performing, and graphs for the temperature values. And we also have the locations controlled by LOD, which creates this effect where we kind of, when we zoom in, we see the farm itself. Where we zoom out, we see the different locations of the farm and the building information model of the farm. And the building information model of the farm, the graphical model that we've included is by including the different parts of the farm itself. So the elevator, the floor, the tunnel bottom, the tunnel roof, and all the different architectural parts of the farm, as we're seeing here. And this is the level 2. So this is the upper level of the farm, where we do some location VR tours and some live streaming of the cameras that we have there. And we're going to visualize the energy and the weather data using the Mapbox API and the cityscape, as we've seen before. So yeah, so this is it, I guess. For the crop version 2, what we're developing now, we're preparing some 4D visualization of tunnels, the predictions, the scenarios. Sorry, I didn't have time to talk a little bit about scenarios, but more or less is about predicting temperature and crop growth. Yes, I think I'm going to wrap up here.
Okay.
Okay, thank you very much.
Thank you very much. I think we've got time for one quick question. So the most popular question on Slido is, what framework or library did you use to make the dashboards and graphs?
We used Chart.js, and we didn't use React or anything like that. We just went directly to JavaScript and HTML.
Okay, and I'm sure anyone who's asked a previous question can ask one of the other questions on there, can contact Flora or anyone else on the project, and they will answer them for you. So as you can see, our blended session will be starting in just over 4 minutes. So we're going to wrap up here. I'd like to say thank you to everybody who's presented in this session. And if you're staying on, then just stay in this call. Thank you very much, everyone.
Yeah.